two new ideas to the dimensional analysis thing. The square and cubic units. So what you do with area and what you do with volume. And then what do you do if you have a complex set of units, like miles per hour, meters per second, grams per milliliter. Some of those units that are something per something else. Let's start with square and cubic units. The problem with square and cubic units is built upon people making a bad assumption. We know that 1 inch is 2.54 centimeters. What that leads to is people making the assumption that if I want to convert square inches and square centimeters, that I can just do this and have a conversion factor that'll work for me. Unfortunately, this is not true. But I need to convince you that that's not true. So to do that, I've got a little 1 inch by 1 inch square in your notes. If I had to calculate the area of this square, I would just take 1 inch times 1 inch, and I don't think anybody would make any arguments that the area of my little square there is 1 square inch. But now let's travel to Europe and take our square with us. When we get to Europe, we run into our European friends who don't like our 1 inch by 1 inch square. They would rather have us say that this square is 2.54 centimeters by 2.54 centimeters. Our European friend doesn't actually want us to change the size of our square, they just want us to change the way that we measure our square. And they would like to calculate the area by doing 2.54 centimeters times 2.54 centimeters and getting some kind of a number. Our European friends say that our square has an area of 6.45 square centimeters. Now, we haven't switched squares. The square is exactly the same square. So it must be the case that 1 square inch is equal to 6.45 square centimeters, which would very definitely make the first statement false. You can't just take a linear conversion factor, slap squareds on the units, and have it work out. But we do need a way to get from a linear conversion factor to an area conversion factor. The way that we could find out that 1 square inch is equivalent to 6.45 square centimeters would be to take the conversion factor we know, 1 inch is 2.54 centimeters, and instead of just putting the squares on the units, if we square everything, we'll get this conversion factor we have here in the green. If we do 1 squared inches squared equals 2.54 squared centimeters squared, we'll land at a conversion that does this in terms of square units. There's nothing more to doing square and cubic units than just squaring or cubing every single piece in the conversion factor. After that, it's just dimensional analysis as usual. So let's try an example. I want to figure out how many cubic decimeters and 3.4 cubic meters. For the information part, we'll start with the relationship between decimeters and meters. 10 decimeters is equal to 1 meter. And if we want to use this in a cubic sort of way, we have to take our conversion factor and cube every single part. 10 cubed is 1,000. Decimeters cubed. 1 cubed is 1. Meters cubed. done that, I can just finish up the dimensional analysis like I usually would. It's going to be a one-step process. Meters squared, meters cubed. The decimeters cubed. 3.4 meters cubed. Put meters cubed on the bottom so it cancels. 1,000 decimeters cubed on the top. 3,400 cubic decimeters. That's it for squareds and cubes. Nothing has changed except that I need to either square or cube my conversion factor before going through with dimensional analysis.
So is a decimeter a tenth of a meter?
A decimeter is a tenth of a meter, yeah. The other thing we need to do today is complex units. This is like miles per hour. The whole key to success with complex units is to just have two separate thoughts. Treat the numerator and the denominator independently. So when you tackle problems like this, what I want you to do is I want you to think about the numerator and do everything you need to do to the numerator, and then stop thinking about the numerator. And then think about the denominator and do everything you need to do to the denominator, and then stop thinking about the denominator, and then solve the problem. Let's try this. Let's say we are driving the speed limit in front of the elementary schools. I want to know how many feet per second I'm traveling if I'm going 15 miles per hour. Let's just have it as two separate thoughts. In the numerator, I need to go from miles to feet. There are 5,280 feet in 1 mile. And then I'm going to stop thinking about the numerator for a minute, and I'm going to think about the denominator. In the denominator, I need to go hours to seconds. 1 hour has 60 minutes, and 1 minute has 60 seconds. And I'm going to build two separate plans. One plan for the numerator, one plan for the denominator. The numerator is pretty easy. I'm going to hop straight from miles to feet. In the denominator, I'm going to have to start in hours. I'm going to hop to minutes, and then to seconds. The real key to success here is how you write the 15 miles per hour. 15 miles per hour means 15 miles over 1 hour. And writing it stacked up like that will make your life a lot simpler. So let's do the numerator first. I've got miles in the numerator. I need to turn that into feet. I'm going to put miles in the denominator in the next step. 5,280 feet. Miles cancels with miles. I did it. There's feet. I'm done with the numerator. Now I'm going to do the denominator. The difference here is that hours is in the bottom. So in the next step, because hours is in the bottom already, I want to put hours in the top. 1 hour is 60 minutes. And hours cancels with hours, because math works at a distance, just like it does right next door. and I want to get rid of minutes. They're in the denominator here. Let's put minutes in the numerator in the next step. Minutes cancel. There's the seconds I was looking for. S feet per second. Now I'm going to do 15. That's 5,280. Divide by 60. Divide by 60. Keeping two significant figures because of the 15 miles per hour. My speed in terms of feet per second is 22 feet per second. The rules of dimensional analysis didn't change. I just had to deal with some units in the numerator and some units in the denominator, and then I proceeded just how we